Hi everyone. So this video of notes and just kind of instruction is going to go over electron configuration. So we're still in unit 2 and this is lesson number 4. So that's where your lesson page is on eClass. So we have been talking about protons, neutrons, and electrons, and we've looked at Bohr models of the atom before. So on your notes, that center, on my screen, it's red. On your paper, it's probably black because it's not printed in color. That area is our nucleus. Okay, now remember, the nucleus of the atom is where the protons and the neutrons are located. Now notice they take up like a very small amount of space compared to all of the orbitals or energy levels where the electrons are located. Okay, and so that first ring is going to be our first energy level. Okay, and then the second ring is our second energy level, which from here on out I'm just gonna write down EL. And then we've got our third energy level, our fourth energy level, our fifth one, and our sixth one, and then the one on the very edge is our seventh energy level. So overall, atoms can have up to 7 energy levels. Now, not every atom has enough electrons to fill them, okay, but those energy levels are where the orbitals are located, and we are going to talk about how the electrons, the pattern that they use to fill in that energy level, because there's an order and a pattern that they follow. So each energy level in an atom is going to contain a different number of electrons. So remember, your electrons are kind of out here. They're all on the energy levels, but they can only hold a certain number, and it goes in a certain order. Now, we've already learned that every period, which is also called a row on the periodic table, so a period or a row on the periodic table represents one of the energy levels in the atom. And we learned about that in lesson number 1, okay? But that electron in the energy level has what we call like a unique address within that atom, and we call it the electron configuration. Now, what I mean by address is I mean that, like, if you want to send something in the mail, then we know that everybody has a unique address. So, for example, for the school, I don't actually know the school's address, but like we all have a number, right? Like a number, and then you have a street name, and then, right, we have Lawrenceville, Georgia, and we've got a zip code. I don't actually know the zip code for Lawrenceville, but you've got your specific address, and you might say apartment C or whatever it is, and your mail will get directly to you. Well, that's kind of what the electron configuration is. It's the address that we use to find where that electron should be located. And each energy level, okay, contains different sections. So we call them our orbitals. Okay, so the energy levels contain a different number and a different type of orbital. I'm sorry, that was a mistake. I didn't mean orbital. I meant a sublevel. So sorry about that if you wrote in pen. So a different sublevel, and the sublevels contain different orbitals. And each orbital can hold 2 electrons, okay? So the electrons on the outer energy level are called the valence electrons. Now again, remember, we introduced that vocabulary word in lesson number 1 when we were talking about the Bohr model. So the electrons on our outer energy level, or the highest one, are called our valence electrons, and it's abbreviated by a V with the E raised to the negative sign, which is our electron symbol. Okay, now when we talk about sublevels, okay, you can imagine that an atom is kind of like a hotel. Okay, so let's say on the hotel you have you know, hold on, let me draw a nice fancy one, right? The kind that get like smaller at the top. Okay, so you have different floors on your hotel, right? A floor in a hotel is like your energy level. Okay, so you have level 1, level 2, level 3, level 4. And when you get on the floor, let's say floor number 1 is shaped like this, where you've got your elevator, and then there's a hallway, and then there are these other hallways. Okay, so each hallway or type of hallway would be like a sub-level. Okay, so this floor would have 3 different hallways. Okay, and then within that hallway, okay, you would have the rooms, right? Or the rooms of the hotel. And inside your room would be your electrons, okay? And a room would be your orbital, okay? Hopefully that kind of analogy makes sense to you. But so when we're thinking about our types of hallways, right, we have our floors. So imagine you're an electron and you're told, okay, your room is either on the first floor, the second floor, the third floor, fourth floor, that sort of thing. And your sublevel, that's like telling you the hallway that it's on, okay? Now, each hallway or sublevel is represented by a letter, S, P, D, and F, okay? And they all have different shapes. So an S sublevel is shaped like a sphere, okay? So it looks like a basketball, okay? The P sublevel is shaped like a dumbbell. Kind of on paper it looks like a figure 8, but it's more like a dumbbell, so it kind of looks like this. It doesn't really connect in the center because that's where the nucleus is, okay? But it looks like that, and there are 3 of them. And then the D sublevel kind of looks like a 4-leaf clover, because it looks like that. And then the F sublevel, it just looks crazy, okay? It's just complicated. They make me want to say F my life because I can't draw them worth anything. So we're not even going to try. Now, you don't have to memorize the shape of these, so don't worry about them, but I did want it in your notes just so that you have an idea. And if you remind me, I will show you a video of how they overlap. But in each sublevel, they can hold a different number of orbitals. So remember, your sublevel is like your hallway, and your orbital is the rooms. So basically, each hallway has a certain amount of rooms on it. So the S sublevel only has 1 orbital, okay? The P sublevel, or the P hallway, can hold up to 3 orbitals, and the D sublevel can hold up to 5, and the F sublevel, its shape is a little crazy, it can hold 7, okay? Now, when we think about the total number of electrons, imagine that the electrons are like the people who are trying to stay in the room, okay? If you have 1 room or 1 orbital, then you can have 2 electrons, okay? So our total number of electrons would be 1 orbital times 2 electrons equals a total of 2 electrons. But in the P sublevel, the total number of electrons would be my 3 orbitals times 2 electrons, which means I can have a total of 6 electrons. For the D sublevel, it would be 5 orbitals times 2 electrons, gives us a total of 10 electrons. And the F sublevel would be 7 times 2 electrons, which gives us 14 electrons. So here we can determine that there are 7 available energy levels, there are 4 sublevels, and their shape and their number of rooms. Okay, now not every energy level has all of the hallways or all of the sublevels. Okay, and so we are going to look at that because you know which energy levels have which ones based on the periodic table. So you're going to want color pencils or a highlighter or something like that right now for your set of notes. But imagine that every box on the periodic table represents a different electron, okay? If you are imagining that, then we know that a row, so remember a row goes side to side like this. So a row, which is also called a period, is also your energy level. Okay, so on our periodic table, we have 1, 2, 3, 4, 5, 6, 7 rows, which correspond to the 7 possible energy levels. Now, these two under here are part of row 6 and 7, and we'll get into that. So if that's where our rows are, or the floors of our hotel, how do we find the hallways or the sublevels? Well, those are in special places in our room. So we are going to highlight, so at the S sublevel on your periodic table is located in the first 2 columns. Okay, so it's organized mostly by our columns. Okay, so these two are S as well as helium. Okay, because it's kind of like helium belongs in this missing spot over here. Okay, and so that is where the S sublevel is on the periodic table. So every electron or box in there will be in the S sublevel. Now the P sublevel, I'm going to highlight those in green on mine. Those are located in columns 13 through 18, again with the exception of helium. Okay, so that is this section over here. So notice that there are 6 boxes in each row. So in our S sublevel, right, like if we just pick any row, there's 1, 2. There's always just 2 boxes, and there were 2 electrons that could fit in the S sublevel. If we count the P sublevel, there's 1, 2, 3. That's not a 3, that's a 6. 1, 2, 3, 4, 5, 6 boxes, and that corresponds to the 6 total electrons that can fit in a P sublevel or a P hallway. Okay, now the D sublevel, I'm going to highlight those in pink. Okay, the pink ones can have a total of 10 electrons, and you might have guessed that that is located right here. So the P or the D sublevel is here. Okay, and then our F sublevel, which I'm going to highlight in blue, can have a total of 14, and those are your 2 rows at the very bottom that are underneath your periodic table. Okay, so those are your sublevels. Now our orbitals. Remember how we said that like the P sublevel can only hold 3 orbitals? Imagine if you were to group these in pairs. So this is 1, 2, 3. It can fit 3 orbitals or 3 groups of 2. Okay. Now, one thing that you want to keep in mind is that the D sublevel, okay, so that's this area right here, okay, our D sublevel, okay, when you're looking at your energy levels, you have to subtract 1 energy level, so make sure that you put this here, so you have to subtract 1 energy level, because electrons fill in the orbitals and the sublevels based on the lowest amount of energy. Like they're really kind of lazy. They don't want to use more energy than they have to. And so when they do that, the shape of our D sublevel, like if you look at this, that shape is a lot more complicated than P. And so it begins to fill in a different order. The F sublevel down here is similar, except it's so complicated that you subtract 2 energy levels. Okay, and so what I mean by that, and I'll show you an example, is if we look over here, okay, it's electron or its ending electron configuration. So when you see something just like this, it's called an ending electron configuration because it's just one part and not the full address. But if we see that, the 4 there, which I guess this whole thing is my ending electron configuration, but the 4 represents the energy level, or rho. The S represents our sublevel that it's located on, and the 2 represents the electron. So if we look at 4s2, that means I'm looking at row number 4, which is right here. I'm looking at the S sublevel, which is purple, and then 4s2 would be located right there in that box. Okay, so whatever element that is, it would have an ending electron configuration of 4s2. Okay, if I wanted to look at all of these, I mean, we could fill them in. It literally just goes in a pattern. So let's see if I can, oops, I didn't want to erase all of the purple. I could start here. This would be 1s1. It's on the first row, it's in the S sublevel, and it's the first box, so it has 1 electron. Helium would be 1s2. Lithium, we're on row 2, but we're still in S, and we're in the first box. Then we're row 2, S, the second box. And we can do that in the P sublevel too. So I kind of have to put my green back. Hold on one moment. But in that first box, I'm still on row number 2, but now I'm in my P sublevel, the first box. 2p2, 2p3, 2p4, 2p5, 2p6. So your electrons basically fill in the spots from the lowest energy level, starting at energy level 1, and then they go up. Now, where that gets complicated is it starts to get complicated in row 4, okay? Because here you have your 3 S's, 3s1, 3s2, and then you have your 3 P's, 3p1, 3p6, okay? But here, this is 4s1. Now, the problem is that your D sublevel, we said you subtract 1 energy level, right? So that means when you get to this first pink box, oh man, when you get to this first pink box, this is actually going to be 3D1. Okay, and the reason why it's there and not on row 3 is because the shape is so complicated that the electrons would rather go up an energy level to row 4 and be in the S sublevel than have to deal with everything going on in the D sublevel on row 3 or energy level 3. So it's kind of like if something is super crazy, you'd rather do a little bit of extra work just to avoid it. And that's kind of what the electrons do. So this is 3D1 and it goes all the way to 3D10. And then once you get back to the P section, it picks back up at 4P1, 4P2, 4P3. So you always have to remember to subtract 1 energy level. For the F sublevel, you subtract 2. So these kind of get put right here. And so, for example, 6s1, 6s2. So row 6 minus 2, this would be 4f. So basically, electrons would rather fill in all of energy level 5 and start a part of energy level 6 before it even touches the F sublevel on energy level 4. Because the shape of F, remember we said, is crazy, and it just doesn't want to deal with that mess. So this would be 4F1 all the way to 4F14. Okay, so that's kind of what happens there. Now, that's just talking about our ending electron configuration, okay? So, but what I want to show you is how we do a full electron configuration. So these are our steps for our full electron configuration. Okay, so what you'll do is the first thing you'll do is you'll calculate the number of electrons. So we are going to look at iron. Now, in order to do this, you need your periodic table in front of you. Your laminated one is perfect for this. If you're in class, you can ask for an expo marker. If you have one, it's great for this. But so you'll calculate the number of electrons that you have and determine which box on the periodic table is its endpoint. The box will not always match the element. So I'm going to put that here. It will not always match the element. Okay, and then you start from row 1, box 1, and you begin to kind of walk across the periodic table. And again, you might be a little confused, but I promise it will make sense in a minute. So the first one we have is iron, which iron is Fe on your periodic table. So we're going to look over here at this periodic table, okay, and you'll see that iron is right here. So our first step, if I'm trying to figure out the electron configuration of iron, is to figure out how many electrons we have. So remember, your electrons are your protons minus the charge, okay? So that's what it says here in your notes. Electrons are equal to the protons minus the charge. So here, when we look at iron, they don't tell us anything about the charge, so that we assume the charge is 0. So that means if my charge is 0, when I'm calculating my electrons, we know that since iron is number 26 on the periodic table, 26 minus 0 gives me 26 electrons. So because that's the case, iron is going to be my last box. And so what we do is we read our periodic table. So remember, we've got the S sublevel is purple. So that would be all of that, including, oops, that shouldn't be green, including helium. We've got our P sublevel here, which I'm not going to take the time to fully color in. We've got our P or D sublevel in the center. And remember, for the D sublevel, we always subtract 1 energy level. Okay? So we have S, P, and D. And, and then F is down here, but we almost never do one. Although, if you want a challenge, you can try to do one from down there. But for iron, we figured it out. So what we do is we start here, okay, and to write the full electron configuration, we're going to walk across each row or period on our periodic table until we get to the box for iron, because iron is number 26 and we have 26 electrons. So when I start at row 1, okay, I write down the row and I write down the sublevel, and then I'm going to put a check mark in every box that I need to go through. So 1 and 2. So that's 1S, 2. And it's completely done. So then I go to row 2. Okay, so I'm at row 2, section S, and there are 2 boxes, number 3 and 4. So that's electron 3, electron 4. Okay, so, and there's 2 of them. And then I keep going across row 2 to over here, and I'm still on row 2, but I'm on a new section now. I'm in the P sublevel. And now I'm going to put electron 5, 6, 7, 8, 9, and 10. And that's 6 of them. Okay, so 2p6. And then I go to my 3rd energy level. And I'm on row 3, section S. And I put 2 of them. Okay, and then I keep going across row 3. And now I'm at where aluminum is. I'm still on row 3, but now I'm in section P. And there's 1, 2, 3, 4, 5, 6 electrons that can fit there. And then I go to row 4, and I'm getting closer to iron. 4s. Now remember, there's only 2 electrons in 4s. Okay, so it's 4s2, because once you get to this part, I'm now in the D sublevel. And even though it's on row 4, in the D sublevel, I have to subtract 1. So that means this is 3D, and then there's 1, 2, 3, 4, 5, 6, and I stop there because I've reached my ending box, so it'd be 3D6. So this whole thing is my answer. Okay, that's my full electron configuration. So let's make sure that we have that in our notes. And you'll notice it gets very repetitive. Okay, so it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6 was our answer for iron. Now, and that was because we had 26 electrons. Now, if you notice, if you were to highlight all of our electrons here, all of those added together, so my exponents added together equal my 26 electrons. So if you know you need 26 electrons, then those should add up, okay? Now, for aluminum with a positive 3 charge. Now remember, if it has positive 3 charge, then this is a cation, okay? And so aluminum is normally has 13 protons. So my electrons would be equal to 13 minus a positive 3. And so that gives us 10 electrons. So that means when I'm writing my electron configuration, okay, when I'm writing my electron configuration, which I'm going to have to erase all of the stuff from iron, okay, when I'm writing this electron configuration, that means instead of stopping here where aluminum is at number 13, I would stop there if I had 13 electrons. But since I only had 10, I'm actually going to stop where neon is, okay? And so for that, that means when I start here, so for aluminum with a positive 3 charge, my electronegativity, or not my electronegativity, excuse me, my electron configuration, I start at row 1, section S, and I'm going to fill in, so I'm just going to put dots this time. So I've got an electron there, and an electron there. So it's 1s, 2. And then I'm go to row 2. 2, I'm at section S, and there are 2 boxes, so 2 electrons can fit. So I put an exponent of a 2. And then I keep going across row 2, and there's enough space for 1, 2, 3, 4, 5, 6 electrons. So it's going to be 2p6, and I stop there because I've put an electron in my final box. And so if I notice, 2 plus 2 plus 6 equals 10 electrons. And so I can see that here. Okay, so let me write that in our notes. So we have, oops. So we have 1s2, 2s2, 2p6. Now remember, our valence electrons, okay? If you have valence electrons, which we reminded ourselves of our definition up here, we said that valence electrons were the electrons on the outer energy level, right? Or the highest energy level. So when you look at an electron configuration, your energy level are these big numbers, right? The 1, the 2, the 2. So the highest one we have is energy level 2 for aluminum. This is the highest energy level, okay? And my electrons are my exponents, so 2 and 6. So that means this atom, this cation of aluminum, would have a total of 8 valence electrons, because 2 plus 6 is 8. If I were to look at iron, okay, and I look at my energy levels. I have 1, 2, 2, 3, 3, 4, 3. The highest one is 4, and there's only 2 electrons in there, so that means this one would have 2 valence electrons. And that's going to be really, really important, because on your practice here, you've got different atoms and ions, and I want you to write your electron configuration, okay? You might want to create your own special column that says the total number of electrons in there as its own separate thing, to make sure that you remember to do that step first. Otherwise, you might go to the wrong spot on the periodic table. And then down here, I want you to use the electron configuration and tell me the number of valence electrons and the identity. Or if I give you the identity, I want you to go backwards and tell me the valence electrons and the electron configuration. Okay, so we're kind of going back and forth in reverse. Okay, so this becomes very easy once you've practiced, but it does take time. So go ahead and begin your practice.